So in this video, I want to take a look at how length contraction gives rise to the Lorentz force law. And again, I'm not going to do a full-on derivation of it because that would be beyond the scope of what I'm trying to do here. But I at least want to motivate how a magnetic field in one person's frame of reference could look like an electric field in another observer's frame of reference. And to kind of set the stage for how this could even possibly be a relativistic effect, I just want to first think about looking at, say, two pea-sized objects about a meter. Let's put them, say, a meter apart. So if these are objects about the size of the pea, roughly there will be about Avogadro's number of protons and electrons in each pea. So if you think about it, that means that every proton here is going to be trying to repel every proton here. So let's just go ahead and draw that in. I'll call that F++. And every electron in here is going to try to repel every electron in here. So I'll call that one F-. And these would be of the same magnitude. Oops. Try that again. These would be of the same magnitude because in both cases the force is going to be equal to K Q over R, where Q is the charge for either the protons or the electrons or whatever. And we'll do this in absolute value because I also want to think about the attractive forces. So then this pea-sized object would also be feeling an attractive force from every proton in this object over here, attracting every electron in this one here. And similarly, there would be another attractive force due to every electron over here attracting every proton over here. So we've got four forces, and all these forces cancel. So these forces cancel. But just for funsies, let's figure out how big is this force. Well, this is going to be K, and then for each one of these Q's, we're going to have roughly Avogadro's number times the fundamental quantum of charge. We'll be doing that again over our distance r, 1 meter. So this will be K NA squared E squared over R. All right. So if you put in the numbers, this is going to be 9 times 10 to the 9 Newton meters squared per Coulomb squared times 6.022 times 10 to the 23rd squared times 1.6 times 10 to the negative 19 coulombs squared over 1 meter. Whoops, squared. All right, so 10 to the negative 19 squared, that's going to give us like 10 to the negative 38. I add 10 to the plus 9s, or times that by 10 plus 9, so 10 to the negative 38 becomes 10 to the negative 29. But 10 to the 23rd squared is 10 to the 46. So 10 to the 46, 10 to the negative 38, that was 10 to the 8, so 10 about 10 to the 17, and then we pick up about another 10 here. This works out very roughly to be about 9 times 10 to the 19 newtons, which is, if you consider that if you have a metric ton of material, the force of gravity on the surface of the Earth of it would be 9.8 thousand newtons. This is on the order of about 10 to the 15 tons of force. So if I have two P's just sitting there a meter apart, this force is 10 to the 15 tons, this force is 10 to the 15 tons, this force is 10 to the 15 tons, and this force here is 10 to the 15 tons. Add them all up and you get 0. But you can see that this is a very delicate thing indeed. And if anything were to go off by just the slightest percentage, like hardly anything, you could easily be left with a few newtons left over, right? So differences on the order of a part in 10 to the 20 could show up. So gammas that are 1 with 19 zeros and a 1 could actually, from a relativity perspective, could actually matter when we're talking, if it could affect the how we measure the charges on something. So even though currents in wires move very slowly, so just for comparison here, if you remember in a wire, the current, a 1 amp current in a wire in, say, a copper wire that is 1 millimeter in diameter. Turns out the drift velocity of the electrons in the wire is about, again, we're not getting too fussy here, but it's about 1/27th of a millimeter per second. So you're talking 10 to the negative 3 meters per second. Call it 10 to the negative 5 for the millimeters, and then you got 1/27th in front. I'll call it 10 to the negative 5 meters per second. That's going to show up in gammas that, although they'll be not that different from 1, that is certainly a lot fewer zeros between the 1, the point, and the other 1 out there somewhere than what would matter to show a non-negligible force. So, believe it or not, even though the wires, the current in the wire, the electrons in the wire are moving very slowly indeed, it turns out that this is actually something that we have to worry about. So let's start worrying about it. So we'll start first in the frame of the wire. So in the frame of the wire, let's say we've got a chunk of wire here. And we'll just imagine that this is an infinitely long wire. It'll make things a little easier as I try to motivate this. Let's just go ahead. We're in the frame of the wire. This is a proper length. We'll say that this chunk of wire here is of length L. And we'll say it's carrying a current I to the right. Alrighty then. So then that means that we have protons that are fixed in place in the wire, and I'm trying to draw the spacing reasonably evenly, like so. And and we'll also have electrons with basically the same spacing. And this is because we're assuming that our wire is electrically neutral. All right, so then these electrons here are what are going to be drifting to the left at our drift velocity. And we showed this earlier, but it's just kind of worth remembering. The current will be equal to the linear density of the charge carriers times our drift velocity. All right, so we've got a current going to the right, so you can go ahead and do the hitchhiker rule with your right hand. Put your right thumb pointing to the right, see how your fingers curl, and what you're going to get are magnetic field lines going around this in circles. I'll just draw one or two of them just to get some sense of it. Oriented. Like so. So if we had a charge in the area moving at, say, V, charge Q moving at V, it would feel a magnetic force equal to QV cross B, like we've seen before. All right. So with that, let's go ahead and think about this now from the frame of the electrons. So in the frame of the electrons are not moving. So what this will mean here is that the spacing of the electrons, as we saw it here where they were moving, by the metric of moving meter sticks are short, in the frame of the electrons themselves, the electrons would say that they're spaced out wider than before. So this would mean that the spacing between electrons would be what it was before times gamma. So since the linear charge density is the charge per unit length, it would mean that the density of my electrons, I'll call that lambda minus, be equal to the density of either of these charges up here over gamma. But also in the frame of the electrons are going to say that it's the protons that are, whoops, I'm trying to keep them evenly spaced. It's the protons that are doing the moving, and they're doing the moving, and they will be the ones moving at the drift velocity. So let's go ahead and mark that there. So to the electrons, these protons are the things moving, and they are drifting to the right. Now, both in the frame of the electrons and the frame of our stationary frame, or the frame of the protons, if you will, we're going to agree the conventional current goes to the right. So before we said negative charge is going to the left, so conventional current right. Here we're saying it's positive charge is right, so conventional current right. But now they're seen as moving. So that means that the spacing between the protons will be what it was before over gamma. So that means that the protons in the frame of the electron will be more closely spaced. So we'll call it lambda plus. So that will be the linear density we had before times gamma. So now what does this mean? If you are a charge sitting out here, let's just say you're a charge in a parallel wire, and you're just going at that drift velocity, so we can keep it all in the same kind of frame. If you're a charge right here, you are seeing an imbalance of charges. You are seeing fewer electrons, lower density of electrons, and a higher density of protons. So you are going to see a net electric field that is pointing out. And so you would feel an electric force. All right, so let's figure out what the strength of this electric field actually is. Yeah. So we can say that the linear charge density that you would observe would be in the frame of the electron. So I'll just call that lambda prime. That would be the positive linear charge density plus the negative linear charge density. Now, since this is a negative quantity here, putting in what we observed, this is going to be lambda. Plus lambda minus. So putting in what we observed before, this is going to be lambda times gamma minus 1 over gamma. And just let me put in this minus sign right here to help keep that straight. Alrighty. So you're going to be, so if we go ahead and put in for what that is, we remember that gamma is 1 over the square root of 1 minus beta squared. And then this is going to be 1 over that, so that's just plain the square root of 1 minus beta squared. So what I'll do is I'll put this on a common denominator. So putting on a common denominator, we'll have lambda times 1 minus, now the common denominator is root 1 minus beta squared. So that means I have to multiply this by 1 minus beta squared in the root again. So this is root 1 minus beta squared squared. So this will be lambda times 1 minus, well, squaring this out, it's going to give me 1 minus beta squared over root 1 minus beta squared. All right, so the ones cancel, and this becomes lambda beta over root 1 minus beta squared. Okay. And if we think back, this was, so this is going to be, beta squared. So this is beta squared times lambda, but then this is 1 over this root is gamma. Gamma lambda we saw was our positive linear charge density, so let's just roll with that. And the reason I'm saying that is because to S prime, since they say the current is due to positive charge carriers going to the right, that current would have to be equal to lambda plus times our drift velocity. All right. So this is going to be, putting that in, lambda prime then is beta squared times I over V. And beta squared is V squared over C squared. So this is IV C squared. Now, this means the electric field that the electron would observe would be equal to lambda prime over 2 pi epsilon naught r. This is just what we got for a long straight wire. And then we can put in our lambda prime to get IV over 2 pi epsilon naught c squared r. Now, we remember that the speed of light is 1 over epsilon naught mu naught. So if I square that, c squared is 1 over epsilon naught mu naught. Or 1 over c squared will just be epsilon naught mu naught in the numerator. So this becomes epsilon naught mu naught IV over 2 pi epsilon naught r, and we can cancel the epsilon naughts. Now we've got V times mu naught I over 2 pi r. Well, holy crap, that's the magnetic field. And if you work the directions out, what you get is that electric field strength would have to be, as a vector, would have to be V cross B. So in the frame of an electron in, say, a parallel wire or something like that, what does it see? It sees an electric field equal to V cross B. And of course there could be some additional electric field as well, just due to stationary charges or something like that. So the total force that some charge would feel would be equal to whatever Q times whatever the local electric field strength is, plus this extra electric field it sees due to the fact that length contraction has changed up the density of the electrons and the protons in the wire, which to us looks like a magnetic field. Alrighty, so in the next series of videos we will be reworking the Galilean transformation to be consistent with everybody measuring the same speed of light, obtaining what's called the Lorentz transformation. Yeah, the same Lorentz. And that will eventually lead us up to E equals mc squared. So catch you over there.